Hi, this video we're gonna discover the mixing chamber. What is the energy conservation for this device? And this is commonly used in our daily life. For example, the shower head, you have hot water and cold water come in and they mix together, come up to the temperature you wanted, right? So in order to discover that, we are going to draw a quick sketch of our mixing chamber. So this is one inlet, this is a second inlet. So they mix together and come up with outlet. So here, inlet, we have M1 dot. The second inlet is M2 dot. And this is our one outlet, okay, M3 dot. So first, our mass conservation. For mass conservation, we learned about it's a summation of all the inlets add together. It's equal to summation of all the outlets together. So for this particular problem, we will have two inlets, M1 dot plus M2 dot. That's going to be equal to this one outlet, M3 dot, right? For this particular mixing chamber. Now let's looking at our energy conservation. The governing equation will be all the energy transfer rate equals to all the energy transfer rate out. And if we were to expand to write down this very lengthy equation, we'll have heat transfer coming. We'll also have work coming. Then we'll plus all the potential inlet mass flow rate H plus half V1 squared plus GZ. And on the right side will be all the outlet. So they potentially have heat coming out and you also have work going out. Then you also have all possible outlet mass flow rate H plus half V squared plus GZ. Okay. Then in order to be specific for this particular two inlet and one outlet chamber, we're going to also make some assumptions here. This is our assumption. Assume. We're going to assume there's no heat transfer. There's no work transfer in or out. There's no kinetic energy change. Neither does potential energy change. And so knowing this, we can go ahead cancel those terms, right? So the only terms left for us to look into, inlet, there are two of them. So it will be M1 times H1. That will be going to be enthalpy coming into this particular inlet. Then there are second inlet, that will be mass flow rate coming to times its respective enthalpy H2 right here. That's our left-hand equation. For our right-hand equation, it's only one outlet, so that would be only mass flow rate 3 coming out with its respective enthalpy, so H3. Then that's our energy conservation equation for this mixing chamber. So this is our mass conservation. This is our energy conservation. If we want to write in another form, we can replace this mass M3 dot with summation of M1 and M2 because that's from our conservation for mass times H3. So then we get this equation as well. Okay, so that is the general equations for mass and energy conservation for mixing chamber. Okay, so imagine if you have 3 inlets and 2 outlets, how would that change? You will have M1 plus M2 plus M3 equal to M4 plus M4, right? There'll be 3 inlets and 2 outlets. So in terms of energy conservation equation, you will have M1 H1 plus M2 H2 plus M3 H3 equal to M4 H4 plus M5 H5. All right, that's it. And I'll see you next time. Bye now.